students, welcome to the next lecture, ninth. Okay, so today we'll continue with the concept of cyclic voltammetry, which we had learned from in the previous video. So this cyclic voltammetry, as we said, is almost similar to the polarography. Okay, so polarography. So here in this we have learned that the first step what we do here in cyclic voltammetry, stripping voltammetry, sorry, SV, stripping voltammetry. So what is the first step we do? Is the deposition of the metal, deposition of the metal here. And in the second step, okay, so this consists of the voltage scan, okay, voltage scan towards the to the electrode, okay, to the electrode that can causes the pre-concentration, so this is what in step 1 we have see the deposition of the metal we do, and in the second step we scan the voltage here that will cause the pre-concentration that or you can say that the metal deposited is going to be displaced, you know. So that is what that stripping voltammetry we perform. So here the main thing in stripping voltammetry is we call it as a trace analytical technique. This is a trace analytical technique which is used to determine the concentration in sub level, okay, I can say sub ppm level. That means in the terms of ppb also you can see that the cyclic voltammetry stripping voltammetry can be performed in ppb level, okay, parts per billion level. And this stripping voltammetry is not recommended. This is not recommended for the sample having the concentration which is exceeding you can say 1 ppm, more than 1 ppm. So you cannot use this stripping voltammetry, okay. So what we can use then, if the analyte concentration is having more than 1 ppm, then you can go for this polarography. This is what the difference between stripping voltammetry and polarography. Almost the same technique, but only thing is what, if the analyte to be interest what we are going to analyze is having the concentration more than ppm, 1 ppm, then you go for polarography. If it is less than 1 ppm to the level of ppb, you can go for stripping voltammetry. So this is what about we learned in the previous video. And one thing, the electrode is hanging mercury drop electrode. This is very much important, we are using in stripping voltammetry. So this is very best because it is having a reproducible surface. This is important, reproducible surface, you can see we are having here. And more sensitive to the factor, very sensitive. So this electrode is very sensitive to the level of 10 to the power of 3 to 10 to the power of 5. So that much level sensitivity is there. And you can see it can detect to the low concentration, very low concentration, that is ppb level, to it is said excellent detection. That's why it is said as excellent detection point limit, excellent detection limit. This stripping voltammetry having to the level of 10 to the power minus 9 to minus 11 mole per liter. Okay, so this is, and sometimes it goes to minus 12 also. The detection excellent detection limit can be detected here. Now if you go for the what we have learned, ASV, that is your anodic stripping voltammetry. So how we perform that, that's having this the container here where you are going to see the electrodes is dipped here, and all these electrodes you can see is being attained with this potentiostat here. And this is your working electrode, okay, and this is your reference electrode, and this is your counter electrode, okay. So this is what, and usually this reference working electrode we use as what, your mercury film, okay. So mercury film is used, and this is your reference electrode, which is a AgCl what we use here. And this counter electrode is usually platinum wire we are going to use here. And this is an analyte we use, and we go for the analysis of the stripping voltammetry. And this analyte now consists of your thing that cadmium and lead, okay. And you are want to detect this metal ion concentration which is less than 1 ppm. So this is how we do it now. And now this is a electrode in a big way, and where this working electrode now is deposited in this way, like this, okay. So this is how deposited here of this analyte, whatever this is there. So we are going to this is called as pre-concentration. We call it as a pre-concentration by using the low voltage. So we are seeing that reduction we are going to do here, where the analyte is going to be is deposited on this mercury, forming an amalgam. mercury amalgam. And after that, so what you say, the same electrode I will take, and when you apply higher potential, that is negative potential, anodic potential, what will happen? They get detached in this way. See here. So analyte, whatever the attached is there, they get detached here. Now here, what we call it as, this is also working electrode here, same thing on high potential. So this is called stripping. This is called your stripping. So whatever attached deposit is there, we are making detached by applying a high voltage. That is a anodic voltage, high voltage. This is a high voltage and this is a low voltage. Okay, so reduction takes place here where it is get deposited here, and we are applying the higher voltage here, and this gets detached, and during this what will happen? It will release the electrons here, and that is detected by the current. That is detected by the current. So that's what oxidation, anodic means oxidation. When it get oxidized, it goes into the analyte here, and while going it will liberate the electron, and that is the current we are going to measure here. And that's why we are plotting here the potential versus time here. In one case we get in this way, like this. Okay, so this is what the straight line where deposition takes place. Okay, here deposition, that is a reduction, mn plus an electron. So you get m here, and this is going to deposit on this electrode in this way. And finally you are applying the high potential here, that is your anodic potential, so where you can get this position. Okay, so this is what you are going to get where the oxidation takes place. Now here the whatever deposited will undergo mn plus n number of electron. This will oxidize, and electron is been liberated here, and that whatever the liberated electron is being applied here now in the another graph here. Okay, and you are going to get here current versus potential, and what will happen here? So according to this you are going to get the peak like this, like this. Okay, so whatever here discharge is there, for example, if this may be the for cadmium +2 and this will be for Pb +2, so whatever you have taken here, so this is how, depending on this, we are going to get the current. So you first apply the potential work, and then you can see the current here. So like this you are going to see the detection will be there for this stripping voltammetry here. Okay, so this is what we learned. And if you see the cathodic stripping voltammetry, okay, this is anodic stripping voltammetry. This process, cathodic is totally mirror image of the ASV. So this is a mirror image, totally quite opposite of the anodic stripping voltammetry here. So here what is happening here? Potential. So you are applying the oxidizing potential. That is a reducing potential here. First step is oxidizing potential. Okay, so you have to do this. So totally it's a reverse of this mirror image, and the species, oxidized species, is stripped from the electrode. Here what happens here? Oxidized species, whatever is there, it is stripped. It is stripped now from the electrode by sweeping the potential, negative potential, by sweeping the negatively potential. So this is what about the what you say, the CSV, that is your cathodic cyclic voltammetry. Now apart from this two, you can see there one more, that is adsorptive stripping voltammetry. We call it as ADSV, adsorptive stripping voltammetry, which is similar to both ASV and CSV, that is anodic stripping voltammetry and cathodic stripping voltammetry. So similar to both, but here one difference is there is a pre-concentration. So this is a difference here. So pre-concentration, so in this case is not controlled by electrolysis. Okay, in this step is not controlled by electrolysis, whereas here it is controlled by electrolysis, but here it is in adsorption, it is not controlled by electrolysis. Here pre-concentration step is whatever we are doing here, the pre-concentration step is, so how you do here is adsorption. Then by adsorption, this is a difference, but done by the adsorption on the electrode, working on the working electrode surface, adsorption on the working electrode surface, or by reaction with chemically modified electrodes. So this is the difference between the adsorption stripping voltammetry with respect to this normal ASV and CSV. Only thing is what here, adsorption to the working surface, the analyte is adsorbed on the working surface or by the chemically modified reaction we are doing it, and rest is same here, so stripping it out. So this is what about the adsorptive type of stripping voltammeter. Now if you come for this application, application of the stripping voltammetry. So in the previous we have seen one or two. So in the previous video here we can see another, that it is used for analysis of the available, that is copper, zinc or manganese content. Okay, copper, zinc or manganese content in soil and vegetable sample, in soil and vegetable sample. So this is what one thing we can see, the application of this stripping voltammetry. Also in determination of food contaminants we can see like toxic metals or toxic metals present in pesticides. Okay, present in pesticides or fertilizer, or sometimes you can see some veterinary drugs. Okay, in veterinary drugs or drug residuals, trace essential components or compounds, trace essential compounds, elements. Okay, then food additives. So this is what dyes. Okay, and some other organic compounds and other organic compounds. Okay, and sometimes in biological significance. So like this you can see the application of the stripping voltammetry can be done like in the soil and vegetable we can see, and even in the food contaminants or toxic elements is very much important, like in pesticides or fertilizers. Okay, and sometimes veterinary drugs residuals. Okay, veterinary drug residuals, so I have written, yes, drug residuals. Okay, veterinary drug residuals. Okay, so this is what. Then sometimes in trace essential elements. Okay, to find out. Then food additives, definitely in food industry. Then dyes. Okay, so dyes also we can use, and sometimes other organic compounds and biological significance. Okay, so these are some of the applications. And if you see, the advantage of this stripping voltammetry is a low cost. So it is having a low cost instrument. This is very much important, low cost instrument. This is the first advantage of the stripping voltammetry. Then followed by, it allow to detect multiple types. This is important, multiple types of dissolved metals in one step. As we have seen, now we have calculated cadmium and copper here in the previous case. So that way, so multiple metal ions can be detected by this stripping voltammetry in one step here. Even the accuracy and fast result. So this having the accuracy and fast result, this is one of the advantage I can say. And sensitive, and it is very sensitive and you can see very selective technique also. It is very sensitive and selective technique, chemical species selective technique. So these are some of the advantage: low cost instrument, detection of the multiple type of metal ions at one step here. Okay, dissolve like we did just now, cadmium and copper. And even it is very fast. Okay, accuracy and very fast result we are going to obtain. And it's very sensitive, this is very much important. And chemical species selective technique, this is very selective technique. But these are some of the advantage I can say of the stripping voltammetry. Now coming to the next, as we have learned in the simple, if I say now, if stripping takes place, okay, by oxidation of accumulated product. What you call for this? Oxidation of accumulated product. That means the electrode is there and you have accumulated here, and you are doing oxidation of this, and you determine the concentration of this analyte. What is that called? That is called ASV. That is your anodic stripping voltammetry. And if the stripping takes place by reduction of accumulated product, I said here oxidation of accumulated product, or if you start with reduction of the accumulated product, okay, accumulated analyte, that is called what? CSV, that is your cathodic stripping voltammetry. So this is what. So in simple, so if I take this metal ion plus Hg in presence of this electron, so what will happen here? I get amalgam. I get a metal amalgam here, and this is what we call it as deposition. This is called deposition step, that is your cathodic, that is your cathodic step. And if you go for reverse here, so this is called determination anodic. You are going to determine the anodic result, okay, reverse of this determination of the anodic current, this is what, okay. So this is how you can see that. And as I said, the graphically like this, if I take, so in some textbook they show, so like this, then they go for like this and like this, and they mention here A, B, C and D, okay. So this they give it as different this one here. So where A is accumulation time, this point is called accumulation time. Accumulation time, at this time the all analyte is going to accumulate on the electrode. This is called accumulation time, where you stir it continuously, repeatedly stirring you do. Then B is the rest period. So then B, this here, from here to here somewhat, okay. So it is a rest period. P is a rest period we call, and C is determining step. Now C means here like this, this is what, this is a determining step. C is your determining step, okay. And D is your anodic dissolution. This is your D, whatever the D is there here. So this is your anodic dissolution, anodic dissolution of mercury electrode, like this, okay. So this is how we show here. Now if you see here, so this I go it as a ED, this is okay. So like this, and here somewhat you can see E naught of CD, potential at which E naught of cadmium, okay. And here we will take it as a copper, like this. Here we will take it as a E naught of copper, Cu, E naught of Cu. As you increase the anodic potential, so here you get the standard electrode potential of cadmium, and at this point you get the standard electrode of the copper. Now if you go down here like this, you can take it down here like this. Here also you can take it down in this way here, okay. And if you draw the another graph here of current, now here current versus potential, now what will happen here? So you are going to get somewhat like this, okay, and here like this, like this, okay. So this is what your IP, this is your IP, this is current potential here. So this is of your copper, here what we got here copper, and this is of your cadmium, like this. This is of your cadmium, where the cadmium is been discharged. Here is a copper, and here this is a copper, like this, copper and cadmium. In this way it is stripped out, and we are going to detect here in this way, okay. So this is how we get. If any other metals mixture is there, again 3-4, like in the previous video I have seen 4 different peaks you are going to get, depending on the potential, okay. How you vary the potential slowly, and how slowly they add whenever there any metal ions is been counteracting, has coming to encounter with this potential, they get discharged here, and you can going to see it is that current is been detected here, and you get a peak here. So obviously here first cadmium is going to get, that's why first peak we get cadmium, then copper, like this. So in this way we can see it is going to work out here in this way, okay. Now here the amount of accumulated metal is sense here. So how you amount of accumulated, this is important, amount of accumulated metal in amalgam, in the amalgam, amount of accumulated metal here, this space, amount of accumulated metal in amalgam, okay. So this is important, can be calculated. How you calculate it? It can be calculated by the concentration of metal in amalgam is equal to current of IACC minus T of ACC divided by volume of Hg into NF. So this is what in the previous video we have taken the formula, where you can say ICC. What is IACC? Is nothing but electrolysis current during accumulation. This is nothing but electrolysis current. IACC, this is IACC, this is nothing but electrolysis current, okay. Electrolysis current during accumulation, and what is this TCC, that is accumulation time. This is your accumulation time, TCC is accumulation time, this one TCC, see, this is accumulation time. Nf, you know, number of electrons. F is a Faraday's constant here, and V is volume. Okay, so volume of hanging mercury electrode, V, this one, of Hg is nothing but volume of hanging mercury electrode, volume taken of hanging mercury electrode. So this is how we can calculate the amount of accumulated product present in the on the electrode. So this equation you can put it and find out the accumulated product. Now if you see the V of Hg, volume of the mercury here, in case of hanging mercury electrode, if you take hanging mercury electrode, so this is a 4 by 3 pi r cube. Okay, so volume is taken as 4 by 3 pi r cube. Now if you take the thin film, if you take now change the electrode to thin film, okay, thin film of mercury electrode, that is your TFME, we call it as a thin film of mercury electrode. If you change this hanging mercury electrode to thin film of mercury electrode, then the volume of Hg changes here to area of the film into thickness of film, into thickness, area into thickness, like this. So volume changes here, so that thing you have to keep in the mind. Okay, so and this ICC, that is current, what we say here, accumulation, that is ICC, that is electrolysis current during accumulation, ICC. Okay, this is determined by the mass transfer of the electrode. ICC is determined by mass transfer of electrode, mass transfer of electrolyte, mass transfer of electrolyte. Okay, mass transfer of the electrolyte and potential at which accumulation takes place. So this is what we can show here. Now pre-concentration of metal, this is what I have shown here you see. So this is what the pre-concentration. Okay, pre-concentration of the metal phase here, this one on the solid surface of the electrode. Then second is electrolysis oxidation potential. This is selective oxidation potential here, what we got here. Okay, so electrode surface, then this selective oxidation potential here of the each metal phase species during anodic here, like this. Okay, okay, during the anodic potential sweeping here. So this is what happens here. So this is how we have to understand here how we can show this. Okay, now if you see the steps here, I will write clearly. Now understand this, I will write the steps here now. Okay, understand the final point here. 4 steps in ASV. 1, what we do here, first solution is stirred. Remember it here, solution is stirred in the first step here. First step, solution is stirred here repeated times. This is important, repeated time, solution is stirred in repeated time. That is called cleaning step. This also is called cleaning step, CLEANING, cleaning step. This is also called as cleaning step. Okay, here the potential is held at more oxidizing potential than the analyte. Remember it here, in this step 1 we are keeping the potential, okay, more oxidizing potential, very more oxidizing potential than analyte. Remember it, then analyte. Okay, so for a period of time, we are using the more oxidizing analyte from the analyte for a period of time. Why we are using this more oxidizing potential at the first step here? Just because to remove it from the electrode, whatever the analyte is present on the electrode, we are removing it. That's a cleansing. So initially whatever the electrode may attach here as a mercury amalgam, so we are removing it in the first step by applying the more oxidizing potential. This is the first step, that's cleaning step we said. Now second, in step 2 what we do, so potential held at low enough now. So here the potential is held very low. Next step we are keeping this potential very low here. Okay, this is what you have to keep in step 2 here, very low enough to reduce the analytic and deposit on the electrode. Now reverse case, now whatever it has been detached here, so in the second step we are making to attach now here. See here, very beautiful. Okay, so in first step very high potential we keep cleansing this, where the electrode become very clean, whatever is there everything goes into the analyte. In the second step we are making it very low, now cathodic type of potential we are applying, so that all thing is again whatever is there, everything that's concentrated, that's called pre-concentration. We are concentrating that metal ions and getting attached now in the electrode, forming the amalgam. So this is what deposit on the electrode now. So this is what the second step we do. And in the third, after second step, stirring is stopped now. So here whatever we do here is in the form of stirring. Okay, in the third step we stop the stirring. Okay, stirring is stopped, and you can see here the except and the here the low potential is allowed to deposit the material and distribute evenly. So this low potential is allowed to distribute evenly on this mercury here. So that is what we do here. And finally, the last step involves the raising of the potential. Again, the last step here, working electrode potential is raised. Last step, okay, we increase the working anodic potential, that is anodic, very anodic we say here. And the stripping oxidizing analyte. So what happens here, it gets stripped now, all whatever the attached will be there, so it is stripped out here. As analyte oxidation, it gives number of electrons. Now here, when the oxidation takes place, the stripped out, the metal ion gives electrons, it gives out the electrons here, and which is ASV, that is this measured by the current. This whatever the electron is left here is measured by the current. So this is how we do it, okay. And you know that this type of stripping voltammetry can be used to detect the microgram per liter concentration of the concentration of the analyte. Okay, so hope you understood this concept of stripping voltammetry. So as much as possible, today I have shown you with very this one, by taking some of the steps here. And here you can see the graph is very much important here, and this graph we have shown today. So how it is been getting here in this graph, stripping and everything, so we have learned today. Okay, so probably this will be the second continuation part of the stripping voltammetry. And yourself you can make a differentiation between anodic stripping voltammetry and cathodic stripping voltammetry with 4 points. Okay, whatever 4 points will be there, so that you can do it yourself by going to these two concepts. And I think that will complete your total knowledge on this stripping voltammetry. Okay, so this is more than sufficient. So I will go for some of the NET questions. If it is occurring on based on this, we will solve that. So in the next video, we'll go for the next concept of the instrumental methods. So be careful with cyclic voltammetry and stripping voltammetry. So these two was there in your syllabus. So we have discussed in two parts. This also in 1 and 2 part we have discussed. Since it is instrumental, so we have to go elaborately. Unless you understand this also we have gone for 2 parts. Stripping voltammetry. Yesterday also we had seen one video. Continuation will be today's video. Similarly here also and here also. Okay. So next video we'll go for the next fresh part of the instrumental methods. Thank you.